Welcome back, everybody. So we often go to the supermarket that is full of food, but a lot of us don't really think about what it takes for that food to get there. I had a conversation with one of my mentors, Gary Rudolph, who's one of our presenters, a number of years ago, and it kind of blew my mind about how much computers and software is involved in our current food production. So after several years of trying to get this together, I finally have Gary Rudolph and Bryce Hemme from Granular to tell us all about that. Enjoy.
Well, great. Thank you, Mark. I'm Gary Rudolph, and I'm joined by Bryce Hemme, and I'm going to dive into some of the rich impact that software has had on agriculture. And then Bryce will cover some of the technologies and solutions that we've used to solve many of our problems, because a lot of our solutions are unique in the space of agriculture, and you can't buy a lot of it off the shelf. So next. So I'm Gary Rudolph. I lead the product organization for Corteva Digital and Granular. And at the same time, at the moment, I'm currently the interim president of Corteva Digital. And I'm joined by Bryce. So Bryce leads our cloud engineering for Corteva Digital and Granular, and also is the head of architecture. So between us, we've built 3 of the leading farming software products in agriculture. And we'll probably talk about one of those in a minute. But we both work for Corteva AgriScience. Maybe just a quick background, because I suspect a few of you might not have heard of it, but it's often described as a 200-year-old ag startup. And basically, we were part of Dow DuPont. It's a 2-century-old company. It was spun out about 3 years ago into Corteva. So we're newly registered on the stock exchange, but we were part of Dow DuPont at one point. And we produce seed and crop protection products. We have about 15 billion in revenue, Fortune 500 company, 21,000 employees over 140 countries. We have some of the second largest brands in agriculture, right behind John Deere with Pioneer. And so that's just a little bit of background to hopefully get a feel for the org we have and a feel for what we are and maybe some of the significance of what we do in the industry. And so agriculture is incredibly important to our world and continues to become even more important. So population growth is expanding. We're surpassing 8 billion people in the planet. We're going to continue on towards 10 billion and obviously can go further on that depending on your perspective. At the same time, we have arguably reached what we call peak agricultural land. So the land dedicated to agriculture has peaked a few years ago. Questions about exactly how much of the land in the world has been used. But that's peak. There's no more land being created as far as agriculture goes. In fact, it'll probably decline as cities and suburbs expand into farmland. That's been decreasing. So this means we need to feed a lot more people, close to 25% more people, probably with the same or likely even less land. And so productivity has to increase with that. And then software is a key component, and digital is a key component to make that happen in the years to come. It may not be widely known, but agriculture has already had a large impact for technology. So we're going to see in the top left is planters and harvesters are all, there's an operator in them, but for years now, even 10s of 15s of years, they've actually been driven by GPS steering, where it'll actually auto steer, guide the equipment across the farm through large swaths and keep them where you keep the spacing appropriate across there and be efficient with the use of it. On the right, you'll also see a lot of monitors inside the cab. Equipment has had a multiple of sensors coming off. So off of as grain is harvested or as we're planting, there's hundreds or 200s of data points coming off every few seconds, including position, how much product is grain being processed. You'll see on the bottom there, specifically, this will matter in a little bit, is there's every row of seed is managed and actually placed in the ground and controlled by the equipment, and the rate of that is controlled by what we call different prescriptions. You can A/B test different seed products that are going in the ground. You can vary that seeding rate depending on the soil composition. You can even have more than one seed type in the equipment as well. Now, all of this is going up in real time these days up into the cloud. You can also use USB sticks, but most of it is actually moving in the direction where it's streaming up within minutes. It's going to hit the cloud systems and be processed to analyze what's happening on your farm or your field. So a lot of technology is being powered, and software is actually behind all of this. Next. So at Corteva, to maybe set the context now, is we built a flagship product called Granular Insights. That helps farmers and their advisors with their agronomic processes. So we saw equipment, but we support farms as large, any size, large to small, depending on if they want to use machinery. We help them with seed choices, planting, nitrogen, crop protection, and chemicals. We help them decide when to harvest, how to analyze and optimize their business to get the most ROI that they can, and actually and follow some of the understand the sustainable practice impact they're going to have on their farm. At the moment, our product is international and already supports US, Canada, and Brazil. And so we'll cover a few different areas, and then we'll get into some of the solutions we have for it. So the first is record keeping and analysis. So the base of our product is handling, processing, and making meaning at an incredibly large amount of machine data files from both USB sticks or the cloud. If you remember earlier, I showed that equipment, all of that data, all those sensors are streaming up into the cloud or coming off or streaming onto a USB stick and then being uploaded off through SneakerNet. There's approximately about 5 petabytes of information that we simplify so that a farmer or their advisor can use to understand and diagnose their yield and their ROI on the field. We handle this at a tremendous amount of scale so later on, if you're looking at different scenarios or understand what occurred on this, we'll cover a few of those in a little bit when Bryce covers some of the systems behind it. We can actually answer in a real-time manner across petabytes of data to get these insights and understanding that a farmer is looking for. On top of that, we also have a lot of reporting where we'll connect to carbon marketplaces. We'll help landowners to understand what's occurring on the field that they might be renting out, as an example as well. Those are all things that are the foundation where we keep track of everything that happens on the field, ideally mapped to machine data that's coming off of equipment into the cloud. Next. So if you remember that equipment I also showed, I talked about there's controlling the amount of seed that's going into the ground or the rate of that coming off the equipment. We actually create the plan and the prescription that equipment executes. What this is showing here is a plan that actually puts the right seed on the right field at the right time, based on prior performance, maybe soil composition, and some of the seed properties. We then create a variable, this is called a variable rate prescription, that defines where the seed goes and at what rate it goes. And the different colors are showing different seeding rates. So there's a lot of process models, a lot of historical data that'll come into play to set this up. That'll then get placed into the equipment and then executed and control what goes into the ground. Next. Similar to this is nitrogen is one of the largest inputs costs to a farm outside of seed and land. It often gets applied, gets over applied. That can cost a farmer more, and then typically has runoff issues that causes an impact or an environment. That's going to only increase with regulation, or as we see dead zones in areas, of course, like the Gulf of Mexico. So every day, we'll go ahead and help, at the beginning of the season, we'll help a farmer create this nitrogen plan and a prescription. It's very similar to what you saw with the seed, but it actually specifies the amount of nitrogen to place on which part of the field, so that in some parts of the field you use less nitrogen, some parts you use more. And then every day we run simulations that will predict the uptake or the loss of nitrogen based on the crop stage, the agronomy of growing, depending on the crop, precipitation, temperature, and soil composition will all affect the use or the loss of nitrogen on the field. And then we help a farmer to understand when they're actually going to be at risk of having too little nitrogen, and we can help them understand that at the right time to monitor that, and actually throughout the season, see if they need to make a second or sometimes even additional applications. All right, and that gives us kind of I just wanted to forgot there's actually yield predict and monitoring. So as well going along with this, we go ahead and also look at using satellite imagery or looking at scanning from ear photometry. We're using the camera on a phone. We'll actually analyze that product of corn, and we'll actually look at from that or imagery. We'll help understand a farmer for what they can expect for yield, how's the yield predicting. We also have imagery that will identify crop issues. So down in the bottom there, you're seeing where we'll understand if there's perhaps an area not growing well. We can then send out a farmer or one of their advisors to go inspect that, and then also use the phone's camera to detect different disease and propose a particular corrective action that they can take to manage that, to help maximize what yield they're having, or look at the ROI of what a treatment might cost. All right. So that kind of gives a high level view of some of the challenges. I just wanted to kind of give the context for this one. And then I want to let Bryce kind of go into some of the technology behind a couple of these examples and go a little bit deeper and maybe talk about some of the solutions we have.
Thanks, Gary. So like Gary said, I'm going to dive into just a few different examples here, get into a little bit of the architecture, why some of this, as well as some of the learnings and things that we have gained as knowledge along the way as we've built out our systems. So first of all, just real brief on architecture. So I could show you a big diagram, probably not going to be overly helpful, but I took a quote that I actually had an article recently about this. And I think it kind of sums up really our back-end approach to architecture today within Corteva digital space. So we can read it here. We follow a serverless first, event-driven approach. And we really rely on AWS for just about everything that we do. And so as much of the heavy lifting as we can, we offload. So we use Lambda very heavily. We've recently been undergoing a migration actually from Kubernetes to pure serverless using Lambda. And then we also leverage things like step functions for orchestration, Kinesis for streaming data. And that's another case where we had gone down the path of Kafka and realized, the cost for maintenance and those types of things was pretty high. We ended up heading in the direction of Kinesis, worked actually with Amazon directly on this because I think many people would say that have tried to use Kinesis. It's not as featureful as a product like Kafka. And so a lot of the things that are newer features in Kinesis are things that us and others were heavily working with Amazon on trying to get implemented. And we started to leverage those. And then Dynamodb is another aspect that we use very heavily. And it allows us to scale a lot of our systems as far as just data processing goes and scale with the demand, which really in agriculture is heavily seasonal. As you would imagine, like Gary was showing, there's a heavy season where planting's going on. There's a heavy season where harvesting's going on. There's a heavy season in between there where other events are occurring. But really, there's a large part of the year where there's not a lot of activity, and it's the winter in North America, or it's the rainy season in Brazil and Latin America, where not a lot of activity is happening in agriculture. And so we need to be able to scale with those demands. And a big part of it for us is how do we make sure that we're not incurring needless costs during those times where we don't have those peak traffic scenarios. So anyways, that's a little bit on our architecture, and I'll dive into more specifics here. And so first thing is, Gary talked about machine data and really how machinery is super advanced in the agriculture space. And everything is really driven by software, and even autonomy is kind of becoming a reality within the space. So we'll talk a little bit about machine data processing and how we approach this. So first off, let's just get real clear on exactly what machine data is. So like Gary had showed, agriculture machinery, they have lots of sensors. They're outfitted with GPS. So in this case here, you can see a machine. This is a planter, probably planting corn or soybeans or something like that. There are a lot of sensors on a machine like this. Every one of those little rows you see has several sensors. And so what that actually results in is something typically on an average field, about 200,000 spatial data points. And so those are data points that have a latitude, longitude, and also have time associated with those. But then in addition, each one of those ends up having sensor readings as well. And so in some cases, up to 200 sensor readings per point. And so you can imagine how much data you start dealing with pretty quickly in those scenarios. And not to mention, just because it's spatial data, it's a little bit more challenging just to work with that in general, especially at that scale. So you can see a map here where it's extremely dense data. There's a lot going on right there in that picture when you really drill in. So the other piece, and Gary kind of alluded to this, but within the ag industry, there's not really a standard data format that is widely adopted. And so data such as what you see in this map might be coming off a machine like you see on the left there, but it might be in a format that's proprietary to somebody like John Deere or another machinery manufacturer. And so that's a situation where we have to interface with a lot of SDKs that those companies provide. Some of those SDKs are very, very outdated, and we'll talk a little bit more about that in a minute. But things such as like VB6, COM still are in existence and still used. Now, that's not the majority. That's very much the minority of the type of data that we deal with and the SDKs we have to deal with. But it is something we have to be able to handle. And so we'll talk about some of that complexity here in a minute. So like I said, to make sense of this data, it needs to be processed into a standard uniform format. So we'll jump into a little bit of some details on how we actually accomplish that. So the first part of this is, you can imagine any distributed system, one of the challenges that you quickly run into is trying to ensure that you're not reprocessing the same thing over and over, or that you're not stepping on each other as you have distributed processing occurring. And also in the scenario where you're dealing with spatial data like we are, we need to be able to identify what pieces of spatial data actually all go together to make a single unit. So like you saw that map on the previous slide, all that data that comes in, it could all be individual points that aren't coming at the same time, could be slices of sets of points. And so we need to bring that all together to make one holistic picture of what actually happened on a single field in that case. And so for this scenario, one of the things we had to do is develop really what we call a spatio-temporal distributed locking system. And so we've leveraged Dynamodb for this. If you've looked at this before in Dynamodb, Amazon publishes an open source framework for this using Java. So it doesn't exactly handle the spatial temporal nature, doesn't exactly handle the specific use case, but it's similar. So it's something we were able to actually pattern this off of. So to talk a little bit about how does this work? So any location on Earth, we need to be able to say, whether in this case, 1 meter by 1 meter, or in the case of maybe it's 1,000 meters by 1,000 meters, or you pick your size of area. We need to be able to say this area is locked for this period of time. And that period of time is the time that an actual operation was occurring on that field. So a tractor was driving over it planting seed, or a harvester was going across that acre. But we know we need to keep that locked so we can actually do a bunch of work on it and not have other processes come in the way and actually also work on that same piece of land. So the way this works is kind of a typically locking scenario. So nothing too crazy, but like I said, we do need to identify the space. We need to identify the time. And so a single client can request a lock for a specific area and time range. And if it's not already locked, you're going to be issued that. Now, client 2 comes in and attempts to acquire the same lock. It's rejected and also given, here's the time and the expiry of that lock. So with that, the client really has to decide what it wants to do in the case of client 2. And as client 1 continues, like I said, can renew that lock, but then eventually as the process completes, they're able to release that lock. So again, this is something that we had to build very specifically to solve a problem of how do you process geospatial data at pretty large scale with a distributed system. As far as how that part of it actually occurs, so I said Lambda was something we really focused heavily on earlier. So in most cases that works extremely well. We'll talk a little bit about, Lambda is what we go to by default, but that doesn't always work. I also mentioned VB6 and COM. Good luck running that on Lambda. But one of the things we do is leverage Lambda to be able to scale out extremely fast and extremely wide. And so in doing that, that really is a big part of the reason why we need to have a pretty strong distributed locking system. And then the other piece of this is really that, with the density of the data, like I showed earlier, we need a way to actually handle that data in a performant manner, because that is a large set of data and we have lots of that coming in all the time that we're trying to process. And so we want to leverage something like GeoJSON, very featureful, flexible type of language and definition. But the problem is it's all very, very verbose. And so we developed something called GeoStream that I'll talk a little bit about. So first thing, like I said, we scale Lambda extremely wide to be able to process this data as needed. All of that's orchestrated by step functions. Step functions really handles the fan out of Lambda and other compute types that we'll talk about. And so that is a big part of this is really scaling wide to be able to process the amount of data that's coming in. But then, like I said, GeoStream. So GeoJSON, if you've worked with spatial data, you probably know what I'm talking about here. Anybody that hasn't worked deeply with spatial data, GeoJSON has a bunch of types built in. One of those is a feature collection. As you can see here, feature collection is really just a set of spatial features with some data tied to it. So in this case, you can see you have points, and for those points, you have some properties. Like I said earlier, the data we get in, those properties can be upwards of about 200 sensor values that we're getting per point. And so in the case of that field I showed earlier, that would have been 200,000 of these features, each one of those with 200 properties. So you can imagine how large that gets really quickly as far as GeoJSON goes. So what can we do about that? what we ended up developing is really what we would refer to as it's truly a lossless compressed GeoJSON-like feature on a binary stream. And so it's really a binary representation of GeoJSON features. And so we've been able to use that to really compress down the data, also make it very efficient to process. And so you're not just reading the strings, not persisting strings, not trying to just compress the strings. You're actually dealing with pure raw binary. The way I would look at this, anybody who's worked with geospatial data, there's a standard called well-known text. And there's also another one called well-known binary. This is the equivalent of well-known binary, but for GeoJSON. So if you're interested, I recommend just check this project out. We've used it now for about 4 years pretty successfully. So the other aspect, then I mentioned step functions. So step functions, if you haven't used step functions, it's quite amazing once you get into it. On the surface, it's really hard to actually understand, how do I actually work with step function, or what value does it provide? But at the core of it, it really offers you a really advanced way to define overall orchestration, and also some really nice things such as guarantees of retry and failures and those types of things. So we use it for a lot of the aspects here, but one of the really interesting parts is targeted compute platform decisions. So I mentioned we have kind of this situation where we have some, what I'd say, outdated heritage or legacy technology that we have to use because it's provided by third parties to process their proprietary data formats. So what we've had to do is really have a decision tree, and step functions allows us to do this, to say, if I can identify the type of data, how I need to actually process the data and read that data, I now can target a specific compute platform and optimize our spend, also optimize our throughput. So it roughly looks like what I've outlined here. So first step, can I target Lambda? If I can, awesome, let's do that. Let's go use Lambda, like I showed earlier. Let's fan that out extremely wide, process as much data as we can through Lambda. But if I can't, we have to actually drop into kind of the next state, which is, can I target really a containerized solution? And so something like Fargate. And so in that case, we use Fargate and we actually spin up tasks. So these are situations where, for whatever reason, the data takes much longer to process, or the dependencies for this don't actually fit nicely into Lambda, those types of things. So we actually are able to target a different type of compute using Fargate. And then the last one is the one where we probably could run all data on this compute platform. It's AWS batch using Windows instances. And so we certainly could run everything on those, but that is extremely cost inefficient. And also, not to mention the maintenance and all the uptime that we would have to have with that infrastructure. So in this case, for things that must run directly on Windows, we're able to send that directly to Windows and spin up nodes as needed to process that data. So again, step functions is really what drives a lot of this and allows us that flexibility and that type of decision without us actually having to write a lot of code to make some of that happen. And so here's just a really basic example of some of our state machines. And these state machines are pretty large. And as you can see, if you haven't used step functions, it's really nice. It maps it all out, allows you to see what that graph looks like of how that state machine is going to function. And you can see all the state transitions. The thing that really is valuable here are some of the things that come for free. Fault tolerance and retries and concurrency constraints are things that we don't even have to think about. They're just kind of baked in, and we can tune the parameters as needed. And then also be able to parallelize a number of workflows is really simple. Again, something we don't have to worry about, something we can offload and let AWS handle for us. So this is a pretty big driver behind most of our architecture, where we have any type of workflows that need to be executed. So you have the machine data. You've gotten this machine data into the system. This is, like I said, highly detailed data that has a lot of valuable information in. Now you have to actually do something with it. And so the next piece is, how do you actually take all of that data once you've gotten it into a standard format and actually make sense of what happened on the farm, and also try to figure out why it happened on the farm. So a little bit of kind of what we mean by this. So I showed some dense data earlier, kind of like you see in the far bottom right there, but that's not it. There's a whole bunch of stuff. If you think about anything spatially and what could happen on a piece of land, especially when I'm farming, there's all kinds of pieces of data that actually matter. So these are things, anything from what is the soil type to what is the imagery looking like, and showing me, in the case of the bottom image here, like what does the vegetation look like on that field on a given date or across a season. These are things like electrical conductivity of the soil, which actually matters quite a bit, and it's a nice proxy for things about the soil. And also there's a number of other things, such as what is the weather, what was the precipitation on any given part of the field, and those types of things. So you have to be able to make sense of all this data. And so if you look at this, as you would imagine, each one of these data sets is varying resolution, different spatial projections, have different tiling schemes, all very different from one another. Some of it's point, some of it's vectors, some of it's raster, and so it's kind of all over the place. And what users actually want, they want instantaneous results. They want to be able to look at any of these data sets, be able to run a query that gives you instantaneous results to tell you what happened on your farm, on any acre, immediately. So very, very dynamic. So an example, if I'm a farmer or I'm an advisor to a farmer and I want to go ask a question, what's an example question? Here's one. Calculate the corn yield grouped by seeding rate and soil type for all acres between a certain time range where there's greater than 150 pounds of nitrogen applied and planting occurred before April 15th. Like, that's a lot of things to start to calculate, especially when it's all spatial data. And so that's the challenge, and something that we've had to solve to actually make our system really valuable to end users. So to get a little bit into how some of that comes together. So first part, and I would say one of the very early decisions we had to make was, what do we do about all this data? It's all spatial data, but really what we're trying to get to is, not only spatial results, but also tabular results. And so to get to some type of consistency, we really had to sit down and come up with a consistent way to look at this data and to get it all into really a common format. One of the main things here is first projection. So what's the spatial projection on how this data is represented on the Earth? And so we did land on Web Mercator as a projection, which I initially personally thought was crazy and had thrown that out. And we went around for a while trying to figure out what the best solution was. And Web Mercator came out to actually be a really good solution for us and has proven to be a great solution for us. And the reason for that is really that it fits nicely with a lot of other systems that you run into when it comes to map. So any of the mapping software that you use typically is showing its maps in Web Mercator. But the other piece of this is it allows us to really just identify one simple coordinate system. And so in our case, it's 1 pixel equals a single coordinate in Web Mercator. And so at the equator, that's roughly 1 meter per pixel. The other thing is it allows us a really well understood, well-known, widely accepted tiling scheme. And so we're able to tile all of our data into 256 by 256 pixel tiles. Now, if you go look at Google Maps and you see tiles coming into the screen as you zoom in and out or pan, those are 256 by 256 pixel tiles. And so that has worked extremely well for us because there's broad support for this and it's well understood. The other piece, which I think for a lot of people seems strange at the outset, is each one of our rasters are single banded. So even though we have a whole bunch of data that all lays over the same area on Earth, we end up creating single banded rasters for each of those. So every single attribute becomes its own raster. So like I showed earlier in the machine data, we have 200 sensors. Each one of those sensors is a separate single banded raster. And there's good reason for that. It comes back to how we're going to process that and how we're going to actually be able to performantly get that data at runtime to actually make sense of it. So then the last bit of this is, now we've agreed on what we're going to process all this data into. We have a plan there, but we need a way to actually go retrieve the data. And so with that, we ended up building a really index of all the raster data that we actually use Postgres for. Many people would think, well, Postgres probably won't scale for that. It actually does pretty good. PostGIS, as I think many people probably are aware of, is the gold standard when it comes to spatial data. But all we're using that for is really the extent of the rasters. And so we know where we have certain types of rasters on Earth. It's not like we're trying to store all these rasters directly in Postgres. The rasters are stored actually in S3. So Postgres is just a pointer. Like I said, it's an index, more or less. So the next piece then is actually coming up with some type of an interface for end users and our software to be able to access this data. And so we really had to step back and think through, how do we want to access this? And some of the common data warehousing themes really play a part in this. So dimensional analysis, that's really what we're after. So as you can see here, we started to develop a dynamic query API. And it's nothing totally crazy or all that unique, but it does give us the ability to have some pretty flexible query patterns. So you can see here kind of an API call as an example. So we have dimensions, we have values, and we have filtering operations. So like I said, very similar to how you would interact with the data warehouse. And so coming back to maybe my earlier point, we can have some very dynamic queries with this approach. And so here's another example of, showing it planting and harvest and moisture by seed hybrid, planting date, harvest date, and soil name for corn in 2017, where I didn't make any money. And so this is a pretty interesting one. Now we can start to get into financials, because we know if you provide it to us, how much you spent on the seed that you put in the ground, or the actual fertility treatment that you put on your field. And we also know if you provide it to us, how much you got paid for the grain that was harvested. So you can start to get into these really flexible scenarios. And so here's just an example, and you can see the data coming back. It's not actually spatial in nature at all. It's actually just plain tabular data, but it gives you all the information about what actually happened given that query. But underlying that's all spatial data using rasters. Now, the last part really comes into, how do we do this though from an infrastructure standpoint and actually make it perform when you have this level of data that you're dealing with? And so I'd say the biggest thing that I think is a little bit of a surprise typically to people is we don't pre-compute anything. So I'll come back to the data warehouse example. In a typical data warehouse, you're pre-computing a lot of things up front. And as you run ETL and those types of things to get data into your warehouse, you're going to pre-compute a lot of the aspects of it. This was something though up front, we made a pretty strong decision, pretty bold decision, I'd say, to really say, we aren't going to pre-compute. Cached invalidation is hard. We're going to mess it up if we do it. And really, we have a flexible system as far as query patterns go. And most of those are probably never going to be used anyway. So there's a little value in pre-computing. And so what we end up having to do then is really dynamically find and aggregate the rasters based on queries that are coming into the system. So that means we need to go retrieve all the different rasters that have the actual values we care about, figure out how we're going to put those together and stitch them together and aggregate the results and send those back to a user quickly, within seconds or sub-second actually. And so part of this, which I think you would kind of imagine, is we have to aggressively cache any query results. If somebody's looking at something for a single field, they're probably going to want to run another query that looks similar or also the same query again for that same field. So we do have a pretty aggressive caching strategy. But then the last part, I think, is really where it gets interesting. So we had to get pretty creative on how we use AWS to do this this fast. So to get into that a little bit, what you'll see here, like I said earlier, again, you'll see Lambda. We use Lambda heavily. But what's a little unique here is how we have these couple layers at the top that are using Fargate. So more stateful containers rather than how Lambda is typically just per execution. And so in this case, we do have an API layer that has, like I said, that cache and has the index. And so that index is able to tell us, what do we actually need to go get out of S3? And also, once we have what we need to get off S3, what do we actually need to do with the results that we get from S3 for those rasters? And then we have this broker layer. This broker layer really is there just to figure out how to best use Lambda to make this extremely fast and efficient to get this data and put it together at runtime and sub-second response times. And so the interesting part here really gets into how Lambda is leveraged. So when Lambda is actually invoked from these brokers, the Lambda functions themselves open a WebSocket back to the broker that actually invoked it. And so I'm sure people are thinking, anybody that's used Lambda, it's like, well, that's really strange. Why would you ever want to do that? And there's a few good reasons. And we admittedly were a little surprised we were able to do this. But part of this is it allows us to ensure we know exactly what Lambdas are alive and available at any given time. So we can issue more work, because if you get one request, you're likely going to get more requests right behind it. And we might as well just reuse the existing hot Lambda that's sitting there already with a connection open and a channel open for communication. And so we have the brokers manage those WebSocket connections. So at any point in time, when we decide we've run these Lambdas long enough, the broker will just drop that WebSocket connection. So there's a little bit of an algorithm built in there to manage that. The other piece of this then is it also allows for us to fan this out extremely wide again. So if I need to get 10 different rasters to actually do the analysis on, I'm able to fan that out as wide as possible and really shard that work on different aspects, such as those 256 by 256 pixel tiles. So I can assign different tiles to different Lambdas and let them go do their work. And then really at the broker, it all gets brought back together and sent back to the user. So this isn't a pattern that AWS promotes. I'm not sure I've ever actually seen this pattern, but it is something that we ended up implementing and has worked extremely well for us. But I'll put the disclaimer out there, use at your own risk. Like I said, not endorsed by Amazon at all. So now we've done analysis. We have data in a format where a user can go actually make some sense of it, identify what happened, and also start to identify why. Now you want to take some action with that and actually change what you're going to do and what the practice or the management practices that you're going to actually use next season. So this is where we get into things like Gary talked about earlier. Soil nitrogen management is a good example of this, and then producing recommendations. So Gary kind of talked through this, but for most crops, nitrogen is one of the most expensive inputs and is a nutrient that's critical to grass-based crops similar to corn and sunflowers. And so this is a situation where you want to optimize the amount you apply and not over-apply. And it also has some pretty big environmental benefits when you actually optimize the amount that you apply. And so what we have to do is we actually have to be able to predict the nitrogen availability and the needs. And we do so using what are typically called crop models. And these are mechanistic models that really simulate the growth of crops. So as you can see on the right, takes into account all the different factors that go into how a crop develops. So that's things such as weather, the genetics, the soil, and also the management practices. And so really with this, a big part of this is running those crop models, be able to simulate scenarios. And so the biggest part of this is these models, they're really good at predicting, a single scenario. But if you have, want to see what happened if the weather was different than what it was this year, what if we try the weather from last year? You want to try all those different scenarios to be able to identify what the different outcomes could be. So in this case, like I said, it's a model that you have to run to actually get some results. And so this model, we ended up developing it in C++ because we need each single execution of the simulation to be extremely fast. And when we say extremely fast, sub 5 milliseconds or less. And so with that, C++ was a really good fit. The challenge there becomes, well, that's not a supported runtime for something like Lambda. And so it becomes a question of where do you want to host that? We ended up taking that model and actually producing Python bindings. And that way we could actually run it easily on a first-class supported runtime on Lambda. And so from there, the next step is really figuring out how do we get the data in, get the data out from all these different model executions that are really, like I said, simulating the crop growth and giving you the results of what would actually have happened. So this becomes really more or less a MapReduce problem, but it's on demand MapReduce. It's not your typical what you would think of as more batch type MapReduce. So in this case, it's a similar pattern like you've seen before. It feels like it's kind of the same pattern we've found to work extremely well across a number of scenarios. But in this case, it really is an API that gets invoked that fans out a number of Lambdas that run these models. And you can think of that API as really the mapper and the model executions, each of those, being a reducer to a degree and running a set of simulations, reducing their results, and then ultimately coming back to the API and the API doing the final reduce and sending the results back to the client. And so in this case, it is another scenario where it is just a matter of really fanning out wide and scaling out wide, and then assimilating the results and sending those back. So Gary showed a little bit of this earlier, but this is really the end result. So what ends up happening is as results are becoming available, they are provided back to the client. So you get more and more detail on what could happen. On the chart on the right, you can see where where on the far right of that chart, you can see there's some uncertainty it would look like. And so these are all the different scenarios of what could possibly happen based on what has happened so far in the year. And so as the crop has developed, we've had nitrogen actually used up by the crop, and it's gone to a number of different places. We've also had nitrogen applied, as you can see kind of by that vertical line there. And then going forward, we don't know yet what's going to happen for the remainder of the season as far as what's the weather going to do. It's always that uncontrollable factor. And so that's where you start to get these results to show really what has happened and what's going to happen. And then the last piece of it is similar to what Gary alluded to, is we're able to produce a map that actually tells you here's what needs to happen on your field. And so each zone has a specific rate that's going to be applied on the field, and the machine will go do that for you once you provide that prescription to the machine. So those are all the scenarios I had planned to cover. So some just real quick key takeaways that we had just got done walking through. So first thing, agriculture must evolve, support humanity, and software is really leading the way in closing those gaps. The heavy lifting can be left to others, so you can focus on what's actually most important to your business and your software product. And that's evidenced through some of the things I shared around really leveraging the cloud provider to do all that heavy lifting and not having to do any of that yourself. And then the other piece here is, AWS and other cloud providers, they are really Lego blocks, as a lot of people like to refer to, but they can be flexed if you get creative. And in a lot of scenarios, like I showed the WebSocket example, that's a scenario of getting creative and kind of flexing that to kind of meet your needs while using a building block that really is provided by the cloud provider and somewhat constrained, actually. Geospatial data, to do this at scale, one of the biggest things that we've learned is agreeing to a base format up front and getting everything into that same format will allow you to continue to scale. If we hadn't done that up front, we'd be continually fighting issues of reprojecting on the fly or trying to, on demand, get all the data into the same spatial alignment. These are things we're able to avoid because it just happens out of the gate. GeoStreams, check it out. If you're really dealing with highly dense geospatial data and features, it has proven at pretty high scale to work efficiently and effectively for us. And then lastly, I know there was a talk earlier today, actually, I think in the same room, about serverless and some of the fine points of serverless. I think that talk was about. But one of the things we have proven to ourselves, and I'm pretty proud of, is serverless solutions can work for high demand environments. It eliminates a lot of other headaches. Now there is some fine print, like I think that earlier talk touched on, where maybe not every scenario, but definitely can flex to meet a lot of the demands that I think has probably gotten a bad rap in the past. It has evolved as an overall technology strategy, and so it is proving to be successful. So that is all I had, and I am going to stop there and hand it back to Mark.
Wow. Who knew that there's so much like computer science happening with agriculture? Just so much data. It's insane. So we have a couple of questions already, and please, I will remind everybody to type your questions into room A so we can ask them. We have about 15 minutes left. Sounds like you're dealing with a ton of data. How do you handle data transfers between lambdas and step functions? I remember step functions have limitations on how much data we can share from one step to the other.
Yeah, that's a great question. That is correct. I've actually run into this recently myself in some work with step functions. And so if you are actually transferring that data as, I guess what I'd say is state, so input, output, yes, going to be problematic. The way we tend to handle that is references to S3 or references to keys in Dynamo. And so one of the two typically is the way we've handled that. And so have your steps or your state transitions, those actually write out the state to one of those data stores and then read it back in the next step. And so what we actually pass in the input and output, it's really just pointers. And so similar to, like I said, the index that identifies rasters, it's all just pointers, really S3 and Dynamo are what's really powering the persistence there.
So stash it away and read it later. That's pretty cool.
Yes.
So Jeremy Beha, one of my coworkers, is has a mind blown emoji. How do you handle grid, unit, acre, neighbor influenced calculations? So if they're like close to each other, next to each other.
Trying to understand the question. Sorry.
So basically, if you have two neighboring points, so to speak, like whatever your unit is, how do you handle any calculations where you say like one is influencing the other, or is it just completely separated by unit? So whatever your unit is, it's just completely isolated from everything else.
Yeah. So if I understand the question correctly, the way we end up doing this is we're binning each one of the points into individual pixels, and then we are only calculating area based on each individual pixel. And so in the case where, and maybe this is what the question's alluding to, maybe not, but in the case where you have multiple points that are going over the same area in the field, and so one issue that you run into with farm machinery is you might run a harvester over an area and then come back over that area again. In that case, we're only counting once. And so we're calculating area based on pixels, not based on area covered by the machine. So not sure I still quite got that question.
Yeah, I didn't. I mean, I don't have. I'm not talking to this person. I have it in chat. From my understanding, it was like, is it like a seepage? Like you make a calculation for one area and like stuff is seeping into the next area. Like how do like nothing is happening in isolation. Like each one of these points is kind of like related to.
One thing a little bit different in ag is some things too. You saw a lot of times. You saw polygons, or we call them zones. So often there's pre-calculated management zones that's based on some other data. So a lot of that aggregation and seepage will happen within that big zone as more of an aggregate calculation itself. I definitely in some of the data science and some of the R&D fields and areas, we'll get some more of sampling further away from one area and blending across it. There's algorithms for that. But a lot of time in the real-time systems, it's about the creation of that management zone and then just projecting that management zone onto the bins of the pixels that Bryce is referring to.
All right, we have another question from Peter. Just curious if you looked at other cloud service providers. Seems there is a parity in services between big cloud service providers, and some are much less expensive for storage and egress.
Yeah, so yes, I have looked at both Azure and Google Cloud. We have invested pretty heavily in AWS, and so it's hard for us to justify a major move there. As far as egress costs, great example where yes, other cloud providers not named AWS have done something there that I think AWS will probably follow suit, I would imagine, at some point to stay competitive. But yeah, egress costs are something that have added up over time. And specifically for us, that's largely been around satellite imagery data. And so that has been expensive. And so we've had to come up with some solutions there to address some of the issues. And some of that is putting in our own egress points and those types of things to manage some of that.
There's a question from Chris. This is more related to the domain you're working in. I know pretty much nothing about agriculture. Are there any introductory resources you would recommend to beginners? Is there anything you have learned about agriculture that you think more people should know about?
One thing I would kind of comment on is I didn't know agriculture very much coming in, and I grew up in the Northeast and the upstate New York, and so I had a different view of maybe precision agriculture coming into it. But there's also this misconception I would just kind of say is a lot of it often is like, oh, big farming or corporate farming. And I'll just generally say that is maybe one of the things that surprised me the most coming into the industry. And this is a little bit off of tech, but there really is not really much of what I would call corporate farming. Almost all farming is still owned by family members, or you look at larger farms, they're still, the whole family is running the operation. And so that was maybe one thing that surprised me quite a bit that I learned coming into the field. There are, I don't know if there's a way to follow up after, because I'm trying to recollect a couple of the books, but there are a couple of different books that talk through the kind of green evolution in farming in the last 20, 30 years. And there's probably a couple cases on the precision ag place that could be some references we could point out if there's a way to do that after, unless Bryce, you happen to familiar with a couple of those now.
I never can remember them off the top of my head.
Yeah.
But yeah, I think we could follow up. There's a Slack channel here, so maybe I can follow up there.
Yeah, there's a Room A Slack channel. You can always type in here or respond to Chris's question in the thread. That would be.
Yep, sounds good.
Cool. And then Abid asks a question. WebSockets with Lambda pattern you talked about, is that proprietary or can this be open source?
It is not proprietary. I'd say that up front. As far as can it be open source, like it could. The reality of it though is it's really basic, and so I'm not sure there's much to actually open source, because essentially what it is we call the Lambda function, and the Lambda function itself, all it does is opens that WebSocket back to the actual broker instance in that case. And so there's not a lot there that I would say is all that unique actually, other than like, I don't think people are actually doing it, but it's very doable and it's not actually that much code. And so as far as that goes, I don't think there's anything really to open source there. It's a good question, something for us to maybe consider if there is something a little bit unique there that we could share further. But yeah, I guess what I would say is, yeah, first thing I would do is go test it yourself and see what you can do. Now the algorithm on how we manage those connections, that's something, I guess maybe that is proprietary. We haven't thought about it that way, but it kind of is to a degree proprietary.
And then Abid just mentioned handling timeouts. I guess there's a question about how do you handle timeouts?
So timeouts of the function. So in the case, and we actually aren't doing this, but in the case where we would have a connection that actually times out at the 15 minutes limit of Lambda, the broker itself has a defined set number of hot Lambdas that it wants to keep. It would just go spin up another one because it would see that I've now dropped a WebSocket connection because a Lambda timed out. I need to go actually initiate another one. And so that would typically be how that would happen. Now, if the question's more so targeted at how do we handle the situation where we're actually doing active processing and we don't get our processing done within those 15 minutes, we very much target our workloads to be under 15 minutes. And if it can't be, then that's where, like I showed the decision tree of different compute solutions, where we're going to fall down to something like Fargate to have more of a long running task for those types of scenarios.
All right. I think this is all the questions that we have. Thank you both so much for giving this talk. And yeah, I mean, like, I had like a conversation with Gary at like a burrito place, and it blew my mind. This is so much more than that. Now I'm just going to be wondering, like, is there going to be enough food? Because it's so low on the hierarchy of needs, right after shelter. So. Oh, yeah. A weird question, but any plans for the Web3 revolution? Web3 revolution, what is that? Does that mean like 3D glasses? The meta?
I assume they mean like blockchain.
Walking through the cornfield and looking at the future yield, you look at you put on your glasses and you see like the corn growing on your.
It's something that's, we joke about it, but also there might be some reality there. And so some of the things that have come up in the past that are somewhat related would be like, yeah, your food supply chain and wanting to understand like the source of the food that, you're putting on the table and be able to actually go back and prove and feel confident that the supply chain is what it is. Those are things that there's been active projects, not just with us, but other organizations as well. I don't know that any of those have actually panned out. Now, when we talk about like true Web3, I think there's something for us to look at there, but not something that's on the immediate horizon.
It mostly internal for a lot of things we do. There's not a lot of added value because it's all there's a tremendous amount of complexity that it doesn't have a benefit to be on chain or be kind of shared out for others to process or use. Where it could be is maybe some of the raw data storage might be something of interest at some point per field as that gets more publicly available. It's still very much, it's kind of locked in, not unlike you would with your cloud storage with, personal cloud storage with iCloud or Google Drive or Dropbox or something, you still generally trust one and go with it. That's the same thing where most ag farmers or most of their partners will still just rely on the cloud provider to keep that for them, because there's a whole lot of value add and complexity behind it. The areas like Bryce mentioned on food traceability definitely is a clear case for it. Also, anything probably to get into commodity trading, or from that space is likely where you'll see transactions and things probably be on some newer solutions like that and more open. But for the most part, a lot of the, you get in, there's also a lot of IP tied up into some of the nitrogen models to even how we handle and process and do some of the analysis. There's IP that it would be really, really hard in most companies to have that be readily made available, or even some of the interim steps.
Yeah, and the cost of nitrogen is about to go up due to the political situation.
Already, if folks, nitrogen's even already doubled prior to some of the recent developments.
Yes. So Peter has a comment, says Elon Musk makes his Tesla money through carbon exchange. Wonder if there's a parallel for agriculture.
Totally. So I touched on this slightly. I did have a slide in there, but I was trying to keep it short to give more room for some of the solutions we have. But we're one of the first meaningful carbon opportunities inside of agriculture. So we've now, I just realized I don't know if I could speak to the number publicly, but we have a large number of our farmers that we work with that, well, actually we'll help them with different sustainable practices, particularly where they switch from using tillage practices to no-till or strip till, where they're just like a portion of the field, or they're using a cover crop. And that allows more sequestration of carbon over a time horizon of like 6 or 7 years into the ground. Now, it requires farmers to change their practice. So someone that was doing tillage or in a non-sustainable manner, if they switch to use a sustainable manner, that will start locking up carbon into the soil. So we help with both the science behind that. We help with our route to market, because we're one of the largest ag companies in the world. And then we also help with the data collection. So all of that record keeping off of the equipment to prove that a farmer did what they said they did. And then we connect that. We also help them model out the price for it, how much they could get paid for it, or how much in every year, because it's not linear. It actually builds up over time. And we help them with that. And then we connect them with marketplace partners like Indigo and such. And then that connects to buyers on the buying side. And this is entirely through the private market, not through government subsidies. But we connect them with it. We can now subsidize farmers and give them another source of income to the carbon, private carbon marketplaces, from large corporate ones, and anyone, whether it's Tesla buying credits, or they would sell, of course, and I guess in most cases, but Pepsi or whomever, Microsoft have been other cases, they'll often buy those credits, and we help with all the science and the connectivity and the route to market and the compliance and data collection that is required for that. That's a product we just launched last year in a very, very small number of farmers. We're ramping it this year, and it's actually something we're well ahead of anybody else in the industry, where it's actually writing checks to farmers. The farmers are actually getting paid now for some of these carbon changes.
Dude, this is incredible. Thank you so much for doing this talk.
Thank you.
Thanks all.